Hi, everybody. So sorry that I couldn't make it to class today, I guess, assuming you watch this on Thursday. I got a little family emergency. I'm actually not even in Washington anymore. I'm back down in California. I'll be here till I think Sunday, and then I'll be back. You can definitely reach out to me while I'm down here. I'll have access to email, my phone, and all that kind of stuff. So if I can help you, definitely let me know. I didn't want to just cancel class though. I thought about having somebody else come in, but I was afraid that wouldn't go well. It might be more of a disruption to you guys than it would actually help. They don't really know what our class is like and what you're used to and all that kind of stuff. So hopefully I'm making the right decision by not having somebody else come in and instead just making a quick video for you. And this video, it's essentially going to be what we would have done in class on Thursday. It'll be a little shorter because in class on Thursday, I probably would have kind of quasi taught some of this material like I do and then gone through the homework. Whereas that doesn't make any sense to do now in a video because I've already taught this material, hopefully better, in the videos that I've made. So you can watch those to get all the information. But I still want to go through the homework with you and talk a little bit about the quiz, the stuff that we normally do in class. So that's what I'm going to do in this video. Hopefully I'll be able to keep it relatively short for you. So first, maybe we'll start with the quiz. I think I talked about this last time in class, meaning Tuesday. But it'll cover kind of two sections, the homework from 2.6 and 2.8, which is the stuff that was due Tuesday. Really what I want you to do here is understand the first and the second derivative. So be able to identify when f prime of x is greater than 0, less than 0, or equal to 0. And when f double prime of x is greater than 0, less than 0, or equal to 0. And really, I want you to be able to do this two different ways. From an equation. So if I give you a function like f of x equals 4x cubed plus 12x squared minus 7x plus 5, don't do it with this exact one because the numbers won't work out nicely, but I'll pick something to work out nicely. And if I ask from the equation, I'll get a function where it's reasonable for you to figure these things out from the first derivative and the second derivative. All right, I'm not trying to give you a problem that nobody's going to get right. And also from the graph. So maybe I should say calculate these intervals or points from the equation and estimate. So from the graph, estimate where f prime of x is greater than 0 or less than 0 or equal to 0, where the second derivative is greater, less than, or equal to 0. And you're like, wait, if I only have the graph and not the equation, how am I going to know anything about the derivative and the second derivative? How can I calculate those? And you can't, right? You won't calculate the first and second derivative. You'll instead use what you know about the first and second derivative, namely that when the first derivative is greater than 0, your graph is increasing. When it's less than 0, your graph is decreasing. And when it's equal to 0, you're at what's called a critical value, or your graph is flat. And when the second derivative, that's supposed to be an x there, is greater than 0, you're concave up. When it's less than 0, you're concave down. And when it's equal to 0, that's a bit of a lie, but we'll call that inflection points. It's really when your derivative switches sign that you have an inflection point. Minor nitpicky difference, but because I'm a teacher, I want to be careful what I tell you. That's what you need to do from 2.6. You won't do both of these. I'll pick one or the other, but make sure you're prepared to do both of those so the quiz goes well. And then there's 2.7. What do I want you to do from 2.7? Well, maybe I'll return to this after I go through the homework problems. But the short idea is I want you to find and classify critical values, see V's critical values using derivative tests. Maybe I won't even say using. Find and classify critical values. And you can use the first derivative test or the second derivative test. I think you'll prefer the second derivative test, but it's up to you. So you'll find your critical values. Be like, I got critical values at 4 and 2. And you'll classify them by saying things like 4 is a local minimum, 2, is that the number I said? I don't know, is a local maximum, that kind of stuff. So you'll find them and classify them as either local minima, local maxima, or neither. In the videos, we talk about absolute minimums and maximums. I don't think I got into that on your quiz for 2.7, but I guess it's not a bad idea to know that. I also went into like endpoints and stuff in the videos. I don't think we get into that either in this quiz, but it's good stuff to know. So anyways, that'll be on your quiz, and I'll try to point those out as we go through. This first problem, we got the graph of y equals f of x. You're just supposed to list all the critical values. Just be able to look at this and find the critical values. And here we are not including the endpoints as critical values. So I guess what I could say is this continues forever in this direction and in this direction. Now there's no endpoints. Or if there are endpoints, we're not including them. So the critical values that are not endpoints, I talked about in the videos how sometimes you include them, sometimes you don't. Generally, we will. But here it says do not include the endpoints? Well, critical values are when my first derivative equals 0. My first derivative equals 0 when the graph is flat. Maybe you can just look at this and tell where the critical values are. It just wants the x coordinates of them. It looks to me like they're at -4, -2, and 0. Done. That's it. Just understanding what a critical value is in terms of its graph. Not too interesting. Question 2, we got another graph. Now we're talking about absolute max, absolute mins, relative max, relative mins, and we are allowing endpoints to be relative extrema. Okay, so absolute max and mins are probably the easiest, right? Note that we only want the x coordinate here. Absolute max is just the highest the graph ever gets. This looks pretty high to me. Absolute min is the lowest the graph ever gets. Looks like right there. Relative maximums are points that are higher than all their neighbors. So you're probably thinking these 2 points, but technically this one counts as well because we are allowing endpoints to be relative extrema. And similarly, relative minima would be points that are lower than all of their neighbors. So you're probably thinking these 2, but we're going to allow this guy also. I just told you the answer. Usually I try to not tell you the answer, but what are you going to do? It's kind of hard to give hints sometimes. Here's another one. We got a graph. We're again allowing endpoints to be relative extrema. You want absolute max, absolute min, relative max, relative min, different graph. Hopefully you can figure all that out. I don't think there's anything too exciting here. You do, I don't know, maybe this is worth pointing out. There is a critical value of this graph that is neither an absolute maximum nor an absolute minimum. That's kind of interesting. See if you can identify that critical value. Question 4, now we're switching from the graph approach to the algebraic approach. Got an equation here. It says it has 2 critical values. Yeah, how do you know that? Well, think about the derivative. It's a polynomial. It's a 3rd degree polynomial. If you take its derivative, you're going to get a 2nd degree polynomial, right? F prime of x equals 6x squared minus 66x plus 60. And what I'm supposed to do is find the critical values. Well, conveniently, all 3 of these are divisible by 6. Hopefully that ends up being the case for you, that they're all divisible by something that makes the leading coefficient 1. That's nice when that happens. Critical values come when your first derivative equals 0. So I set this equal to 0. Maybe I get rid of this or something. And I solve. 6 is never equal to 0. You can ignore this 6. Think divide both sides of the equation by 6. So it's really just when is x squared minus 11x plus 10 equal to 0. Maybe you can factor this to get your solutions. You'll get 2 solutions. Put the smaller number here and the greater number here. Easy enough. Question 5 is a lot like question 4, except now it's not a polynomial. But I think that that's okay. I think that this specific function you'll be able to deal with. I don't know. See how it goes. Take the derivative of this and put that in right here. There's f prime of x. Solve f prime of x equals 0 to determine the critical values of f. Okay, maybe I should do it. I don't know. I'm conflicted whether I should do this for you or let you have a shot at it on your own. I think you can do this on your own. Little hint, you're going to use the product rule here. So you'll get something that'll have an e to the negative x squared 32 with some stuff here. I don't know. I guess that squiggle represents some stuff. Plus some other stuff. And I think you'll get another e to the negative x squared over 32. Right, so when you take the derivative, f prime of x, I probably should have just done it for you. You'll get something times e to this plus something times e to this. My hint is factor out that e. Right, do e to the negative x squared over 32. Factor that out in front. So you get this mess plus this mess. I don't think I've ever scribbled on a problem before. You get that plus that. Why does that help? Well, because you want to take your first derivative and set it equal to 0. And when you have a product of things equaling 0, that's a good place to be in math. Right? If either of these are 0, you get a solution. This is never 0. This can't be 0. It's an important property of exponentials that they can't be equal to 0. There's nothing you can raise e up to get 0 to come out. Right? You might think e to the 0 power is 0, but it's not. E to the 0 power is 1. There's no value x can be that'll make this equal to 0. So essentially, for the sake of critical values, you can ignore that. You're just taking this part, setting it equal to 0. You should get a critical value or critical values, and you'll put them right there. Question 6, kind of the same idea, except we're starting with a different function, right? Here's some practice with exponentials. Here's some practice with logs. I think this derivative will be a little bit easier for you to take. when you take the derivative. I think all the logs will go away when you take the derivative, which will be kind of nice. You'll have an equation that hopefully you can solve. You get those solutions and you put them right here. So not a whole lot to say on this one. It's a good problem. Question 7, more of the same. When are we going to switch to something else? I guess what I wanted to do is give you a variety of functions so you can flex your calculus muscle, right? Take a lot of derivatives. For the specific derivative, I don't know, maybe quotient rule. And then set it equal to 0 and solve. And what you'll get when you, what you'll get for your first derivative using the quotient rule is kind of messy, right? But it'll look like a fraction. You'll get something, sure, I'm squiggling today. You get something divided by something squared when you use the quotient rule, right? And you got to think about when this equals 0. Well, a fraction equals 0 when the top equals 0. You don't care about the bottom. So just take the top, squiggles, I guess, set it equal to 0 and solve. And for the sake of critical values, the x plus 6 squared that you'll find in the denominator, hopefully you see where that's coming from, won't come into play at all. You can ignore it. Take the top, set it equal to 0, get your critical values, put them right here. Cool, moving right along. Question 8. You're given this function. You have to find the first derivative. And then it says, notice that g prime of x equals 0 when x equals 5. In other words, g prime of 5 equals 0. So x equals 5 is a critical value. Okay, so the idea here is you take the first derivative, and then in theory, the next step is to find the critical values. But I didn't want you to have to find the critical values of the first derivative because you'd end up factoring something without a leading coefficient of 1. And I think that would test the algebraic knowledge of some of you guys and drive the rest of you crazy. So I'm just telling you the critical values. X equals 5 is a critical value. You could have found that by taking this answer and setting it equal to 0, but you don't have to because your kind teacher is doing that for you. Now, we want to know whether there's a local minimum or a local maximum at x equals 5. So we're going to use the second derivative test, right? This one is kind of like the quiz, sort of. And that you take the derivative and you find the critical values. In this case, I found them for you. And then you classify those critical values as local minima or local maxima. So you take the second derivative. Right, you got the first derivative, take the second derivative, easy enough because it's just a polynomial. Then you plug in 5. If a positive number comes out, that means this is concave up. If a negative number comes out, that means this is concave down. If you have a critical value when it's concave up, think that picture. If you have a critical value when it's concave down, think that picture. This picture, we got a local min. This picture, we got a local max. On the quiz, I'd ask you to figure this out, right? I'd ask you to classify that critical value as a local minimum or a local maximum, and you'd go through and do all this work. This problem, you don't even have to. Based on the sign of this number, does this mean the graph is concave up or concave down? You can choose between the two. If it's positive, concave up. If it's negative, concave down. Based on the concavity of g of x at x equals 5, does this mean there's a local minimum or a local maximum at x equals 5? At x equals 5, there is a, well, it's positive, min, negative, max. So the idea with this one is it's similar to the quiz, but I kind of walk you through it more than I'm going to do on the quiz. Right? This is supposed to like show you all the steps. This is more the learning process, whereas on the quiz, you'll be demonstrating what you know how to do. But it's similar to this process. I think it's a polynomial if I remember right. Here's another problem, another polynomial. What we're doing here, we are talking about absolute maximums and minimums. So what you got to do is look at critical values and endpoints, or if you're classifying endpoints as critical values, but make sure you add the endpoints in there. So for critical values, take the first derivative, set it equal to 0, and solve. And you'll get some answer there. I think you only get 1. And then also consider -3 and +2. And probably the easiest thing to do is just take the critical value, -3 and 2, and plug all 3 of those into this machine and see what numbers come out. And whichever one yields the largest number is your absolute maximum. And whichever one yields the smallest number is your absolute minimum. The x value would be what you're putting into the machine, the -3, the 2, or the critical value. And this value is, this is the y value that goes here and here. That's what came out, right? So the largest number that comes out, you're writing that largest number here. The smallest number that comes out, you're writing that number right here. Good thing to do, good to understand endpoints and all that. Not really what you're doing on the quiz. Question 10. We got this function. It has one local minimum and one local maximum. That's nice. I mean, I didn't have to tell you that, but I did. The local minimum is with the value of, the local maximum is with the value of. No endpoints to deal with. First derivative, set it equal to 0, solve, you'll get 2 answers. Classify those as local minimums or local maximums. Probably want to use the second derivative test. The local min goes here, the local max comes here. And then take that local min and put it into this function and see what comes out. Right, so if this were 3, whatever f of 3 is what you're going to put down here. I doubt this is 3. If it is, I'm just really, really lucky. But that's how you figure out what goes in these boxes. And then question 11, more of the same, except now my function, instead of being a polynomial, is, I don't know, a power function. I don't know what you'd call this. 4x, a rational function maybe. 4x plus 4x to the negative 1 power. But the good news is the process is the same, right? Take the first derivative, set it equal to 0, and solve. Get those critical values, there'll probably be 2 of them, and classify them. One will be a local min, one will be a local max. Put the x that's a local min here, x that's a local max here, and then the corresponding y values here and here. And you do it again. Question 12. The nice thing about this one is there's only one critical value. So you could expand this all out, but I think it'll be a lot easier if you use the chain rule here to take the first derivative. I think this will be a lot easier to solve for the critical value. There's just one of them. Figure out what it is, put it here, then use the second derivative, classify it as local min, local max, or neither. Straightforward enough. 13. Man, there's a lot of these. Here's your polynomial. For this function, there are 3 critical values, a, b, and c. So you take the first derivative and you're going to set it equal to 0. You're like, whoa, 5th degree polynomial. That means my first derivative is going to be a 4th degree polynomial. That's true. But it's okay. Because what will happen is you'll get, I guess I can do it, 60x to the 4th plus, these numbers, 180x to the 3rd minus whatever 360 times 3 is, 1080 maybe, x squared plus 0. But look, now I can factor out x squared from each of these guys. And I got 60x squared plus 180x minus 1080. All right, if I pull out that x squared. And now it's just a second degree polynomial. So this is what I'm going to set equal to 0. Well, if x equals 0, I'll get one solution. So it sure sounds like one of my critical values is going to be 0. And the other 2 I'll get from taking this and setting it equal to 0. Whoa, the leading coefficient 60. That's going to be so hard. Nah, all 3 of these terms are divisible by 60. So divide all 3 of these by 60 and we'll get 60 times x squared, sure, times x squared plus 30x minus whatever 1080 divided by 60 is, whatever 108 divided by 6 is. Can I do that in my head? I probably could, but I'm tired. I'm not going to. You can get some number here. You can figure that out. Doesn't even help, right? Your numbers are probably going to be different. Anyways, you'll get 2 critical values, right? 1 from this and then 2 from this. And you'll write those critical values here, here, and here, smallest, medium, largest. And then you'll use your second derivative test to figure out whether these critical values are local mins, local maxes, or neither. Then moving on to question 14. I think it's exact same format as question 13. It's just a different looking function. Right? So to take the first derivative, you'll have to use the product rule. And when you use the product rule, you'll get something that's kind of messy. You'll have a mix of x's and e to the x's in there. But much like what we saw before when we were in that situation, I can find it. Here it is. Much like this problem, where we had the squiggles and then the e to the x things, and we could factor out the e to the x things, and this can't be 0, so we get no solutions there. The same thing will happen down here. All right, so take the derivative. You'll end up with 2 terms. Each of those terms will have an e to the 5x in them. Factor out that e to the 5x, and you'll have this. All right, and this will be a polynomial. So set that equal to 0. Your solutions, this never equals 0, so you get no solution. So it's just when the polynomial equals 0, you have 2 answers. You'll put them here and here, smaller, larger, and then take the second derivative. Since it's in this form, it won't be too bad. If you try to take the second derivative in the form it's in, it might be a little harder, but in this form, it won't be too bad. And with the second derivative, plug in numbers, figure out local mins, local maxes, and you're done. 15, most annoying problem on the homework. Here is me rewarding you for watching this whole video if you made it to the end. Because 15, I'm going to get so many emails about it. There's a problem with the problem. Like, I know what I'm doing and it's saying it's wrong. How many critical points does the function have? I mean, clearly it has a critical point whenever the function's flat. So like up here is 1 and there's 2 and there's 3. It must be 3. I put in 3, it said it was wrong. I probably won't get emails because you'll be able to get it wrong twice and check the solutions. You'll be like, weird. It says that the answer is 4. But it's not 4. I mean, maybe there's a problem. There must be something going on up here that I can't see. There's a problem with this problem. Who cares? It's 4. I'm moving on. The problem's not broke. The problem's right. What's going on here is this is not the function. This is the derivative. Right? This is not f. This is f prime of x. So to find critical values, you're not looking for when the graph is flat. Critical values happen when f prime of x equals 0. So this is not a critical value. A critical value of my function f of x happens when f prime of x equals 0. So there, 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 and there. That's why the answer is 4. If this were f that was pictured, if it said the above is the graph of the function f, how many critical points does it have? Your answer would 100% be 3. 1, 2, 3. But it's not. This is not the function. It's the derivative. So you get 4. A little bit tricky. Hope that's helpful. I'm going to end this video here. Sorry for not having class. If you need anything, reach out to me. Otherwise, I hope you guys have good weekends, and I will see you when I get back.